I'm Luke Harris, and this is my Physics 2211 Lab 1 constant velocity. The main purpose of this lab is to use Newton's second law to compare an object's movement to the computational model of it. Through the usage of those models, we'll be able to demonstrate the momentum principle. Describing the models for this lab, first I uploaded a video pushing a cart to tracker, and then I was going frame by frame to get the points for the cart and track its movement. Then using GlowScript, I was able to make a computational model for the cart, and then I compared both the results of the experimental and the computational model. The main fundamental principle for this lab is Newton's second law, or the momentum principle. Momentum is the tendency of an object to keep moving once it is in motion. Furthermore, if the net force is zero, then momentum is constant. And we can use these formulas to aid in our lab. We first have Newton's second law. We have the definition of momentum. We have average velocity. We have velocity update, position update, and momentum update formulas as well. So what to expect is this lab will show proof of Newton's second law in action, as both the expected and experimental values should be similar and should show a constant velocity. So our initial conditions, the mass of the cart is 0.5 kilograms. The initial position starts at 0, meters, and the initial velocity is 0.5500 meters per second. And as you can see, that's how we calculated it from the average velocity formula. So for stuff that we can assume, we can figure out that there's no acceleration on the cart, and if there's no acceleration, then there's no force, which means that velocity will remain constant throughout the entirety of the experiment. We can also assume that we are not accounting for any air resistance or frictional force in doing our calculations and doing our computational model. Secondly, this experiment, the system is the cart, and then the surroundings are the earth and the track that the cart is on. So what I did here is I used the tracker and I took the position frame by frame of the cart as it was going along the track. And then using that, I was able to make that graph that we see in the top left, or sorry, top right, that gives the position over time. So here's my GlowScript code. So we have the initial conditions with the mass, the initial position, and the initial velocity. We have the time starting at 0 in our time step. And then below it, we have our force being 0 because there's no net force. And this is all in our calculation loop. And we have the velocity update formula and then the position update formula below it. Using that GlowScript code, I was able to make these graphs showing the position versus time, the velocity versus time graph, as well as a visual model showing the object going in a straight line. Using both my computational model and the experimental data, I was able to put them into an Excel sheet and make this graph to compare the two. And as you can see, they're both very similar, both linear and constant, which is what we assumed would be the case whenever we started the experiment. So what are reasons of error that could have made mistakes for the graphs being slightly different from one another? The first is human error, since I had to manually go frame by frame to mark the position of the cart, which could cause some discrepancies, and it's not perfect. The model predictions could be different due to the outside forces acting in the cart, because in the computational model, we assume no outside forces, but in real life, friction, and there could be some air resistance to make the velocity and position different than predicted. And the track could also have messed up the data if it wasn't perfectly flat or it had rough spots or potential obstacles that could cause data error. So what if we were to flip the axes, what would be different? So the direction of the cart would change since we're flipping the axes. This means the cart would now be heading in a negative direction. This also mean that the velocity of the cart is changing. However, the speed would remain the same because flipping the axes only changes the direction, not how fast the cart is going. So what does it mean? Is it possible for us to calculate the net force? So it's hard to determine the net force on the cart because of the outside forces acting. But using a free body diagram right here, we can see that the net force isn't exactly 0. So looking at this free body diagram when the cart's in motion, there's obviously gravity pushing down on the cart. We have the normal force pushing up on the cart, and we have the frictional force pulling it backwards. And so the net force would not exactly be 0 as we assumed in our models. However, it's hard to fully tell what it is.